Our topic today is going to be solutions. So we probably have an idea of what solutions are on a day-to-day basis, but in chemistry, solutions have a very specific set of circumstances for them to be classified as solutions. So aqueous is a state of matter, and what that means is something has been dissolved in something else. So we see that commonly if you put sugar into water, or if you put, say, Kool-Aid into water, or if you put salt into water, those things seem to disappear. So you can't tell the difference between a glass of pure water and a glass of salt water that you just sprinkled some salt into. They don't look any different. They only taste different because you can taste sodium ions. So the solution needs to be something that has one object dissolved into another. It needs to be a homogeneous mixture, which means it is a mixture that you can't tell. So that salt water looks the same at the top and the bottom. Kool-Aid should look the same at the top and the bottom, and you need to be able to see through it. There shouldn't be anything floating on top of it, like in orange juice, you might have flecks of the pulp floating on top or settling out at the bottom. Those aren't solutions because they've got objects floating around inside of them. The molecules will never separate. So if I have a glass of salt water and I have a lid on it, so the water can't evaporate, you will never have salt settled at the bottom. The solution concentration won't change. In a bottle of alcohol like vodka, at no point is the top more alcoholic than the bottom because they're dissolved into each other. The idea that the molecules themselves can interact more strongly than gravity can pull them apart based off of density, that's what is keeping them dissolved. That is what's keeping them mixed evenly. The amount of interaction between those two objects, so let's say table salt and water, allows those NAs and CLs that are floating around inside of the water to stay basically completely chaotic and for all practical purposes evenly distributed throughout the entire solution. The particles are also going to be too small to diffract light. If you take a flashlight to the Columbia River or a creek or something and you shine it in, or if you turn your headlights on during a foggy evening, you will see something. You'll see the light. And what's happening is, if you're shining the flashlight into the Columbia, it'll only go so deep into the water. It won't go all the way to the bottom. Like maybe if you're at Crater Lake, you could get it to go much deeper, although not to the bottom because that's a really deep lake. If you went to certain creeks, well, there's a place over not too far away from Mount Hood called Little Crater Lake on 26, maybe, I don't know, maybe 20 minutes from Mount Hood, or from Meadows on Mount Hood. You can look it up, and it's pretty cool that it's this close, and you can see to the bottom very clearly. That's because that is more of a solution than most normal bodies of water that are out there. So when you shine it through the Columbia, the flashlight through the Columbia, particles of, I don't know, bird poop and fish guts and particulate from plants and whatnot, mud, they block the light, they reflect the light back to you. So the only way you're able to see the light is the light has hit an object and then that light is reflected back to you. Same thing with fog. The reason that the light, your headlights become blinding to you is because they're hitting the water molecules in a liquidy form, and those water molecules are bouncing the light back to you. And so you can see it. And if it, under normal circumstances, if it's not foggy, you do not see the beam of light coming out of your car because there isn't any objects for it to hit and come back to you. So that's the other, another aspect of the solution. It needs to be clear, perfectly clear. So we need to make sure that we understand the difference between a couple of words, clear and colorless. Sometimes we use those things interchangeably, but they shouldn't be. Clear just means you can see through it, but that doesn't mean there isn't color in it. So like a stained glass window that's green, you can still see through the stained glass window. Or sunglasses are smoky, browny, kind of grayish. Looking through them, they pull some of the light or block some of the light from getting to you. But they definitely change colors. There's red ones, there's yellow ones, there's blue ones. But what you're doing is looking through, and that's fine. It's clear, but it's not colorless. But the glasses that I'm wearing right now are colorless. They have no, there is no color within them. So clear and colorless is a thing. That would be like water, but just clear, that would be more like Kool-Aid. You can see through it, but it definitely has color to it. And so a solution can be colored. It just, and that's totally fine, but it has to be clear. Two other terms to be familiar with are solute and solvent. So the solvent is the solute or the substance that's there in higher concentration. There is nothing else to it. So if I mix two things together, whichever one I have more of is going to be called the solvent, and whichever one I have less of will be the solute. So usually water or the liquid will end up being the solvent, but not always. So if I take that table salt and I put it into the water is the solvent, and the salt is the solvent. Sorry, the solute that got dissolved. I'll give you an example of this. Alcohol is sold as its concentrations in proof. And so 200 proof for some reason means 100% alcohol. We would call that Everclear or moonshine, and it's terrible stuff for lots of reasons. One, it would be incredibly painful to drink, and two, it's ridiculously flammable, more flammable than gasoline. So I wouldn't, even just putting a little bit of water in it. I mean, this is why one of the reasons on our hand sanitizer lab that 100% alcohol is not used as a hand sanitizer, because it's way, way too flammable. Even just putting 10% water in makes it much, much less flammable. So I will tell you that from that lab, the feedback I gave, the rum is a very high alcohol concentration solution. So it's typically about 150 proof, which makes it 75% alcohol. And at that point, at about 75% alcohol, that's when an alcohol water mixture will burn. So at a 40% mixture like vodka, which is 80 proof, there is too much water. So if I put a match into vodka, it will go out, because even though the ethanol wants to burn, before I can burn the ethanol, I have to boil the water off. And I don't have enough energy with the match and the ethanol that wants to burn to boil the water off and burn the next ethanol molecule. That doesn't happen until I get to around 70–75%, which would be rum. So I'll tell you a funny story that was maybe 15 years old. My brother was playing a video game where he was throwing these Molotov cocktails at the computer game tanks. So a Molotov cocktail is a bottle filled with a flammable solution and a rag in the top. You light the rag on fire, and then you chuck the bottle, and the bottle explodes, and then everything catches on fire. Okay, that's fine. So, but it was snowing, and it sounded like from the voices from the game, it sounded like he was in Russia. So I asked him, and he's like, yeah, I'm in Russia here. And I'm like, so what are you throwing? And he said, bottles of alcohol. And I go, go over to the bottles. And it turns out the bottles were vodka. And I'm like, well, I'm sorry, I hate to tell you this, but vodka's not flammable in that way. You know, he was like, all right, well, great, works in the game. So if you need to, for some reason, throw a Molotov cocktail, vodka is not the solution of choice to make that work for you. Too much water. So I want to talk a little bit about the dissolving process. So what does it mean when something dissolves? It means that that object becomes completely surrounded by water molecules, and then it has actually changed state, whether it's a liquid I put in, a gas I put in, or a solid I put in. Once it's dissolved in there, it's surrounded by water molecules, and now it's in the aqueous state. So if I put table salt in water, a solid solute going into liquid water, the table salt breaks apart the crystal. So that's why you can't see it anymore, because it's too small to be seen. So if you're in an airplane and you're looking down on a city, you will probably not be able to see people. But if you get closer to it, or if you bunch people up. So I flew over Washington, D.C. one time when I was leaving Baltimore from BWI. And as I left, I could see people on the mall, which is that big grassy area around the Washington Monument. And the reason I could see those people is because there were 1 million people there, at least. It was a 1 million-man march happening. So because they were all bunched together, I could see them. But when I came back, I looked down at the mall and I couldn't see anybody. I mean, there were definitely people down there because it was a nice day, but I couldn't see them because they were too far apart from each other. And that's what happens with salt when you dump it into water. So if I sprinkle salt into water, the crystals that I used to be able to see are lots and lots and lots of NaCl stuck together, but then the water pulls them apart. And when they get pulled apart, now I can't see them anymore because I need to have a bunch of them clumped up to see them. Even that tiny, tiny salt crystal that I'm looking at still has trillions upon trillions of NaCl stuck together, and the water molecules pull them all apart. Okay, so here's an example of NaCl crystal. So I have my Cl's, my green ones, and my Na's, my blue ones. And then I've got water molecules here. What you're looking at is something called the space filling model. So here's an oxygen, and then it kind of looks like Mickey Mouse. Not a great drawer, but that's what we get here. So the water molecule itself is bent. And so this is what the water molecule looks like. And the circles around it and the bubbles around it are basically the electrons that are surrounding those atoms. So I have an oxygen and a hydrogen in this water molecule. And what's happened is this little sodium, let's switch colors here. Let's go with white. This sodium atom right here is, as you can see, surrounded by water molecules. You see that? Oxygen, but specifically the oxygen side of the water molecule. Why? Because in a water molecule, this side of the molecule is negative and the hydrogen side of the molecule is positive. So the water molecules go in with their, if they're going to hit a sodium, they're going to go in with their oxygen side and pull them apart. So now what I have is this sodium atom has now been separated from the rest of this molecule. And as a group, I could see those things, but as I pull them apart, I am no longer able to see them. And what you'll also see is this is the hydrogen side of the water molecules. And what I have here is my chlorine. So it's the other side of the water molecule that's going to attack the chlorine, because in this chemical reaction of NAs and Cls, if I look at the oxidation states, sodium is a +1 and chlorine is a -1. So the positive side water molecule, the hydrogen side, would like to interact with the chlorines, and then the negative side oxygen of the water molecule would like to interact with the sodiums. So what's happening is the water molecules are getting plucked apart and then surrounded by water molecules. Sorry, the sodium chloride, the table salt, is getting plucked apart by the water molecules and being surrounded by them. So this sodium right here would be considered aqueous. It has been separated out from the rest and it is surrounded by water molecules. Okay, so for ionic substances, I want to make something super clear. So ionic substances are compounds that are composed of cations and anions, usually a metal and a non-metal, but not always. Could be two polyatomic ions, but it has ions in it. We're going to see the solid form of it, and we're going to see aqueous forms of it. So table salt can be solid or it can be dissolved in water. What we're not going to see is gaseous table salt. We're not going to see liquid table salt. So when you sprinkle table salt into water, it doesn't become liquefied. To do that, you would have to heat it to, I think it's somewhere around 1700 degrees Fahrenheit. So that's not a possibility. And gaseous, you're going up a couple of more 100 degrees to turn it into a gas. So for the ionic substances like table salt or like copper 2 sulfate, I'm going to need to, you're going to need to write those states as either solid or aqueous, because you're not going to see them as a gas. You're not going to see these guys as a liquid. So remember that when you're putting ionic substance labels of states. So let's talk a little bit more about solubility rules and ionic solubility. So I have a list here, and the list works to let you know what ionic substances will dissolve in water, because not all ionic substances dissolve in water. So something like chalk, calcium carbonate, if you put a piece of chalk in water, it just sits there and does absolutely nothing. It does not dissolve. It was a solid when I put it in there, and it stays a solid when it's in the water. So it's just a wet solid, but it's still a solid. On the other hand, table salt, as we know, when it can be a solid, but once it gets wet, it turns into aqueous. It dissolves. Okay. So the reason that we're looking at this, we need to look at this list is because we want to know what dissolves under what circumstances. And so what's important to realize about this list is the rules that are higher on the list supersede rules that are lower on the list. So if I've got some situation where there are two conflicting statements, whichever statement is higher wins. So let's go through some examples so we understand what's going on here. All right, so group 1A metals and ammonium compounds are solid. So if I look at my periodic table, group 1 starts with lithium, goes down to francium. So all of those things are soluble. And that's just a rule. If it's got Na on it, it will dissolve. And the same thing goes with ammonium compounds, which was the polyatomic ion NH4. So if you see a substance and it has NH4 in it or any of those group 1 metals, when it goes into water, it will dissolve. Acids are soluble. So for our purposes, if you see something that starts with an H, it will dissolve in water. Okay, the next one, acetates, perchlorates, chlorates, and nitrates. All of these things are going to be soluble. So if it's got a CH3COO, or it's got a I don't know, I wrote ClO4, or a ClO3, or an NO3. Any of these substances, it doesn't matter what the cation is, as long as those are the anions. If one of those is the anion, then that thing's going to dissolve. Okay, so these are, these first three right here are all solubility rules, talking about things that are soluble. The next one is an insolubility rule. So silver, lead, and mercury 1 compounds are insoluble. All right, so what does that mean? It means if I have silver chloride, that silver chloride, when it goes into water, will behave like the calcium carbonate. It will not dissolve. It will stay a solid. Same situation happens with lead chloride or mercury 1 chloride. They're all insoluble, meaning the water molecule cannot pull them apart, cannot make them aqueous. All right, so the next one here is a solubility rule. So chlorides, bromides, and iodides are soluble. Okay, so if I got any of those on a substance, it's soluble. So hopefully you're paying attention. You realize, well, wait a second, this one right here has a chlorine on it. Why does that rule not apply? It doesn't apply because the silver rule comes first. And the silver says, we are going to stay stuck together, even though the chloride would like to not stay stuck together. So since the silver rule is higher, it overrules the chloride rule, which says I want to separate from you when I go into water. Alrighty. The next one is an insolubility rule. So there's a lot of polyatomic ions here. So carbonates and hydroxides, oxides, phosphates, silicates, and sulfides are all insoluble. So the one you know the best would be, I don't want to use that one, would be oxides. So that would be rust. So Fe2O3 is iron 3 oxide. That's just regular old rust. If you take something that's rusty and you put it in water, it just sits there. It doesn't dissolve it. It just stays there as a rusty thing. If you see like a rusting metal object in water, you'll see a trail simply because water moved it of that rust colored, well, rust at the bottom of a creek or whatnot. It doesn't dissolve like table salt does. There's just particles of rust floating around or laying at the bottom. So that's the situation with all of these. I can give an example of NaHCO3. All right, so there's a carbonate, but this is baking soda and is fully soluble. Why is this soluble? Because my sodium is rule number 1. So because my sodium is rule number 1, even though the carbonate wants to stay stuck together, the sodium's like, catch you later, and just leaves, and it is gone. So it's going to dissolve because its rule is more important. And the last one here is a solubility rule about sulfates, with the exception of barium and calcium. So if I've got, let's say, zinc sulfate, that's going to dissolve in water. Why? Zinc is not on this list anywhere. There is nowhere on here, so I don't have a rule for it, but the sulfates are soluble. So that would separate in water. That would turn into zinc ion plus sulfate anions. Okay. But what if I change the zinc out to calcium? Then the same thing isn't going to happen. Calcium sulfate. So this rule here says sulfates want to be soluble, but I've also got a problem that it won't because of the calcium. So if the sulfate is connected to a calcium, then it will not let go and it'll stay a solid. So if that goes into water, it just sinks to the bottom and does not dissolve. Alrighty, so we want to talk about reactions that happen in water next. Why reactions in water? Why is that important? Well, first off, we do a lot of reactions inside of a chemistry lab with water, so that would be important. But more importantly than that is we drink water. We are giant bags of water. So if it's dissolved in water, we want to know about it. We don't want certain things to be dissolved in our water. If you've seen the movie Aaron Brockovich, I don't want hexavalent chromium in my water because it does all kinds of terrible things to my body. So I'm going to show you 3 different ways to write chemical reactions that happen. And so here we go. They're the molecular equation, the full ionic equation, and the net ionic equation. So this is sort of like a, I know it's not going to look like it, but this is sort of the lazy way. This is the everything is being shown way. And this is what actually happened. So lazy, the not lazy way, and the what happened here. There's a lot going on, but what was the end result? What actually happened? All right, so let's look at why this works out like this. So what we have here is lithium fluoride, and this lithium fluoride is going to be mixed with silver nitrate. Okay, so I've got 2 containers. I've got a container that's got some lithium ions and fluoride ions floating around. So why are they dissolved? Well, it says it's aqueous right here, so they're already dissolved. And why would this dissolve? I don't have a fluoride rule, but I have a group 1 metal rule that says those things dissolve. So the lithium definitely dissolves because it's a group 1 metal. Okay. And then I have another container, and in the other container, I have dissolved some silver nitrate to form those 2 ions. How do I know it dissolved? Aqueous. I know it's going to dissolve because rule number, I want to just scroll back up here. This says I'm going to be insoluble, but the rule right above it, nitrates, says those things are soluble. So the nitrate wins over the silver. The nitrate wants to let go more than the silver wants to stay stuck together. Okay, so I take these things and then I dump them into another container. So now I have this situation where I have lithiums and fluorides floating around, able to bump into silvers and nitrates. Okay. So what happens when these 2 things bump into each other? And the answer is nothing, because they're both positively charged, so they just ricochet off of each other. Same situation down here, both negative, so they ricochet off of each other. What happens when these 2 guys bump into each other? Well, the lithium is soluble because of group 1 or rule number 1, and the nitrate is soluble because of rule number 3. So nothing happens. They bump into each other and they just ricochet off. They both want to be soluble. But when these 2 things bump into each other, they actually form silver fluoride solid, which is a precipitate. So these 2 guys come together, and then this yellow powder is immediately generated and then falls to the bottom as a solid. So that's why it says solid right here, but it says aqueous here. So this is the lazy way to write this, even though I'm seeing a lot of information, because what's really going on is anytime I see an aqueous next to something, they've already separated out. So the lithium is lithium aqueous ion. The fluoride is fluoride aqueous ion. So I have to separate those things out in my full ionic equation. Again, the silver nitrate, we're saying it's been dissolved already. And here we have the silver as itself dissolved and by itself, surrounded by water molecules. And the same situation with the nitrate. You're dissolved. You're all by yourself, surrounded by water molecules. Okay, but the arrow means that now they've been mixed together. And when then that happens, the silvers and the fluorides run into each other and they form a solid. But what didn't change? Well, the answer to that is this is lithium plus aqueous. Lithium plus aqueous. Nitrate minus aqueous. Nitrate minus aqueous. So the lithium and the nitrate had nothing about them change during the course of this chemical reaction. So we call those things that did not change spectator ions, meaning they sat around and watched a chemical reaction happen, but they themselves did not partake in that chemical reaction. Okay, so that answers our question about what actually happened, which is what the net ionic equation is. What actually occurred? Well, nothing happened with the lithium, nothing happened with the nitrate, nothing happened with the lithium, nothing happened with the nitrate. And so I just bring everything down. All of this stuff gets written by itself. So I know that the silver was aqueous, the fluoride was aqueous, and when they came together, they made this silver fluoride. So my net ionic equation is telling me exactly what occurred in this particular chemical reaction. I don't need to know about the spectator ions because they didn't do anything, so it doesn't matter. And that's all I got for this one. Thank you.